Hi, this is Sudeep Panchanda from Quite Easily Done, and welcome to another videos from Know Your Boards. In the Know Your Components series, we had talked of a component which is called the 555 timer IC, which is an 8-pin IC. When we were studying about this IC, we had said that this 555 timer IC can be used in 3 different modes. The first being the A-stable mode, where the output of the 555 timer would not be stable in 0 or 1, so it does not have any stable state, and so the output would keep flipping from 0 to 1 and then coming back from 1 to 0, and will keep on going on this cycle. The next state we had talked of was a monostable mode, in which we said only one state of the 555 timer would be stable, which is the state 0 or the off state, and when we provide a trigger to it, the 555 timer's output would jump from the 0 state to the 1 state, will remain there for a while because it's an unstable state, and will fall back to its original stable state of 0. So we'll get a good nice pulse as an output. And then the last we talked of was a bistable state, wherein the 0 and 1 state of the 555 timer both will be stable. So when we are at the 0 state and we provide a trigger, the output would jump to 1, will remain at 1 till when we don't provide a reset input to the 555 timer, which would cause it to go back to 0. In this video, we would be talking about the 555 timer in the monostable state. We will be looking at the board which implements this solution. First, we will going to look at the demonstration of it, and then we'll deep dive into the circuit diagram. So let's get started. Here we're looking at the board which implements the 555 timer in the monostable mode. Up top we have is the power supply, the VCC or the positive terminal being the red wire, the black one being the ground. On the left bottom over here we have is the button which can be used to trigger the output, and similarly on the top we have is the pin which can be used to provide a trigger via an external sensor. So right now the 555 timer is powered on and is stable in the 0 state. If I use the switch over there to trigger it, we would be seeing the state, the LED glowing and the state moving to 1. We would see that after a while the state is going to fall back to 0. So let's do that. So you see when I triggered it, the output went to 1, and it will remain 1 for a while and then came back to 0. The amount of time it's going to remain in the on state is defined by the resistor over here, which is the potentiometer. If I change the value of the potentiometer, the length of the time for which the output is going to remain on the 1 state is going to be defined. So we will look at the circuit diagram and understand how it is functioning and how is the value of the resistance actually changing the duration of the on state. Let's have a look at the circuit diagram. Alright, so here we're looking at the circuit diagram for a monostable 555 timer. Sorry, the circuit might look complex, but if you break down it into pieces, it will be very easy for us to understand it. So try being with me. Let's first look at the right top corner, which is the 555 timer's pin 3. The pin 3 of the 555 timer is the output pin. And like we had seen in the bistable mode of a 555 timer, this output is connected via a resistor to an LED, and then obviously so this is the positive output, and then we have a ground, and the same is also given to the output header pins that we had seen on the board. So this section on the top right is simply the output. Then we have the pin 8 and the pin 1, which are the power supplies, again similar to what we had seen in the bistable 555. The pin 5 is the control voltage. We always add a capacitor over here for noise filtering purposes, but we're not practically using this pin. We're just ensuring it's grounded and has a noise filter to it. In this case, we would not be using the reset pin. If you remember from the bistable 555 circuit diagram, we had a switch on the pin 4, the reset pin. In this case, we're just putting the reset on plus VCC or plus 5 volt supply because we will not be using the reset functionalities of the 555. So that And then again, like before, we have the pin 2 at trigger, which by default is always on the high or the plus VCC plus 5 volt wire resistor. So by default the trigger is always at the plus 5 volts, and when we press this switch it comes to a grounded state. So by actually giving a 0 volts to the pin 2 of the trigger, the pin 2 trigger of the 555 timer, we actually do a trigger. And this BC547 transistor is just a way in which we were able to have the trigger input pin, in which if the trigger input pin was given a logic high via sensor or any other device, then it switches on this transistor and does the same equivalent thing as the was for pressing on the switch. So this section on the pin 2 is just the trigger mechanism. The trigger happens when we put the pin 2 to 0 volts ground, and high or plus 5 volts is when there is no trigger. So the only main thing that has to be focused now on is the pin 6 and pin 7. If we see both of them are connected together, what we see over here on the right bottom is a potentiometer, a variable resistor connected with a capacitor, and this capacitor is grounded on one side, and the potentiometer is connected to the power supply. This resistor and a capacitor together forms what we call is an RC circuit. An RC circuit is a resistor and a capacitor which can be connected in parallel or series. In this case it is series, which helps us to charge the capacitor slowly and again discharge it slowly. So if we can understand the capacitor better if we go through the Know Your Components series video dedicated to the capacitors. So very quickly, if I go to Wikipedia and show you, this is the circuit diagram for a series RC circuit if you're individually pulling it out of the 555 circuit over here. What it does is it has a unique characteristic which shows us that the capacitor would get charged slowly, and when it is getting charged it starts having a potential difference accumulated across it. So, and the amount of time that it takes for it to reach to that saturation state over here is defined by the calculation which says time is equal to RC, where R is the resistance value and C is the capacitance value. So that is all we would be interested in knowing about the RC circuit. So this is the resistor, this is the capacitance. The multiplication of the two values would give us the amount of time that the capacitor is going to take to charge. The reason why this is important for us to understand is if you look, the capacitor is connected to the discharge pin and the threshold also. So the potential difference across the capacitor would define what is the input at the trigger. By default, if you and the discharge, I'm just going to explain that very quickly in a minute. Let's talk of a state where nothing is pressed and we just assemble the circuit. In that case, that is the state where the comparator 2, which is the right one over here. Sorry, let's talk of the comparator 1 first. The left comparator has an input of 1/3 VCC, which is equivalent to 1.667 volts on the non-inverting terminal. The inverting terminal has the input equal to the trigger, and we had set that to VCC when we are not pressing the button. And the comparator now, because it's comparing 1.667 volts with 5 volts, would give us an output of 0. Let's say the output right now was 0 because we have not done anything right now. So what happens in that case is when the output is 0, the output, not the inverse of the output, is what is fed to a NPN transistor over here. So this transistor is on when or conducting when the output is 0. So when that happens, our discharge pin over here is connected to ground. Okay, so let's go back to the circuit. When we are saying that the output is 0, or we just assembled the circuit, we have not triggered it, our discharge pin is connected to ground. So which means this point over here, this junction over here is grounded. So there is no charging of the capacitor. All we are, so because pin 7 is grounded, practically pin 6 is also grounded. So the threshold we gonna get is 0 volts, which the comparator 2 is comparing with 2 by 3 VCC or 3.334 volts. Now it's comparing 3.334 volts on the non-inverting terminal over here and 0 volts on the non-inverting terminal. Sorry, 3.33 volts on the inverting terminal and 0 volts on the non-inverting terminal, which gives us a 0 output for the reset of the flip-flop. So the output, as we know the truth table of the SR flip-flop, with both comparators giving a 0 output, there will be no change in the state. So it's going to remain as it is. Now let's say we go over here and press this trigger button. What it does is, when we do the trigger, this is similar to what we had done for the bistable mode. When we press the trigger button, we get a 0 volt on the trigger pin, right? That's what we are saying is triggering. Now the input to the comparator 1's inverting terminal becomes 0 volt. So now it's comparing 1.667 volts on the non-inverting terminal and 0 volts on the inverting terminal, which gives us a 1 out. 1 is the comparator 1's output. 1 is the set for the flip-flop, so the flip-flop gets set and we get an output of 1. So as soon as we get the output of 1, the transistor over here closes. You see, now the discharge is not connected with the ground. Like coming back to the circuit, when the discharge is not connected to ground, we practically have is this circuit standalone, where now we have a VCC, a resistor and a capacitor in series. So the current would start flowing from VCC via the resistor to the capacitor, and as we had looked on the graph in Wikipedia, this capacitor would start getting charged and potential difference would start coming in across it. The amount of time it takes to charge to a particular level would depend on the value of the capacitor and the resistor, which said the time for it to come to a saturation level is equal to RC. So now let's say the charging started happening. We started from a threshold level of 0 volts, and just to again show you, the potential difference across the capacitor is equal to the input at the trigger, the threshold, the pin 6 of the 555 timer. So now the charging has started happening, and slowly and steadily this charging would start from 0.001 volts to 0.5 volts, 1 volt, 2 volt. As soon as it crosses the 3.334 volt mark, and let's say it comes to 3.335 volt mark, the comparator 2 is now comparing 3.335 volts on the non-inverting terminal and 3.334 on the inverting terminal, which would give us a 1 output or a logic high output on the comparator 2, which is here, which is the input to the reset of the flip-flop. So the flip-flop would get reset. As soon as it gets reset, our output becomes 0. So the final output becomes 0. Because the output is 0 and we giving an inverse of output to the transistor over here, this transistor becomes open, and again the discharge and the ground gets connected. So as soon as this discharge is again connected to the ground, this capacitor would start getting discharged via the pin 7, and we would again reach to a stage which is where this capacitor is totally discharged and the threshold becomes 0 volts, which is we come to a stage over here again. So this is how we have the 555 timer, which would remain in a stable state of 0 till when a trigger is not provided. As soon as the trigger provided is, we come to this stage where the output would become 1 and would remain 1 till when the capacitor does not charge enough that the potential across it becomes just a bit greater than 2 by 3 VCC. So this time that it took for the capacitor to charge and give us a voltage above the 2 by 3 VCC is the amount of time for which we would be able to see the output as 1 by the 555 timer. And as we said, the time required for it to charge is dependent on the resistor and capacitor. So indirectly, by the values of the resistor over here, which we are setting by the potentiometer, and the capacitor, we are able to define how long will the output remain 1 once a trigger is provided. So that is the circuit diagram for 555 timer monostable mode. Thank you very much for watching the video. We would love to hear your comments and feedbacks. So please write down to us in the comment section below. Let us know of your feedbacks, your questions. Would really love to have an interaction with you and understand how are you feeling about these projects. Thank you very much.